Yeah, so this is going to be a talk about the scientific highlights of gravity. I will have to start from the beginning, of course, and still tell you, I mean, I promise to talk about other things than the galactic center, but this is, of course, the major highlight. So you will also hear news from the galactic center, of course. You cannot talk really about gravity without also talking about the people behind it and in front of it, really. So gravity, it's an instrument, but it's also, in the meantime, it's kind of a community, you can say. And the core team of gravity is made of about 100 people, approximately. Most of them you see here in the picture, even so some of them have only their noses shown, but yeah, so this is the majority of us. We belong to several institutes. So there is in Paris, there is the Paris Observatory. In particular with LESIA, the Laboratory for Space Instrumentation, they contribute to a major part with instruments. Then there is the Max Planck Institute for Extraterrestrial Physics in Garching, that's where I belong to. This is also the group led by Reinhard Genzel here, who, as you know, received 2 years ago the Nobel Prize for precisely the discovery made with gravity. Then there is the IPAC in Grenoble, the Institute for Planetary Sciences and Astrophysics. And then, of course, ESO, the European Southern Observatory in Garching, the headquarters, and in Santiago, the capital of Chile, there is the other branch, so to say. Then there is another Max Planck Institute in Heidelberg. There is SIM in Portugal and PH1 in Cologne. And all these different people and laboratories contribute with instruments and scientists, with engineers, with observers, theoreticians. So there's really a large and very diverse community, so to say. Now, gravity. To really understand gravity, we have to quickly mentally travel to Chile. And actually, I realized something. You know these pictures very well, don't you? Because precisely when I made these pictures in 2019, there were 3 brave guys from Opava University visiting me precisely there, precisely then. Jiří Dobrý and his 2 colleagues, they went on a road trip. They went to observe the solar eclipse in 2019 in Chile. Road trip through the Atacama Desert and visiting Paranal. So you probably all saw that documentary film, maybe even several times. I remember I saw the sequence where Jiří Dobrý is waiting at the gate and he's checking his clock, his wristwatch, and he says, "Oh, she's 5 minutes late. And, oh no, she's 10 minutes late. She's 20 minutes late. Is she going to come at all?" And the reason was that I was so late is I didn't know they were standing at the gate. I was sitting here in the left image, in the middle of the desert on the gravel, having my breakfast coffee in the middle of the afternoon because I was on a night shift. And there is no connection here. There is Wi-Fi inside the building, but outside there is no cell phone connection and nothing. So only when I went in after my coffee, the reception said, somebody is waiting, you have to go. So I ran out, and that's why in this documentary, very embarrassingly, you see me running into the frame, rather out of breath, because we are here at 2,000 meters above sea level. It's not something very extraordinary. You can do that in the Alps and then in other places. But when you actually are here and you work here, you start to feel it. And you feel it mostly also because the air is absolutely dry. It is usually around 10% air humidity. So the Atacama Desert is indeed the driest place on Earth. And sometimes when you're lucky or unlucky, I don't know, the air humidity can drop down to 1%. So it gets really, really difficult to breathe. It's like breathing in knives or something. It's interesting, I have to say. And then, so that's the base camp. And at night, then you go up, or if you're an engineer, you go up during the day, of course. But I usually went up to the peak here, which is on 2,600 meters above sea levels. You go up to this terrace. You can walk up in an hour or 45 minutes, depending on your fitness level. And then you are here on the right side on this platform, and you see these really, really impressive 4 unit telescopes. I should have put here some human for size, but they're really gigantic. They have 8-meter mirrors inside them. Here, one is already open, the others are still closed. And then there is a second set of 4 telescopes, which are called auxiliary telescopes. These are the little ones here with the round domes. When they open at night, they look like little Pac-Man. And they behave a little bit like that, because you can move them around on these rails, on these tracks, back and forth. Each of them has a around 1.8 meter telescope. And the reason you can move these little telescopes around is that you can have different baselines or different distances among them for different targets. The unit telescopes, however, they are solid, they're fixed on the ground. And what gravity now does, it combines the light of all 4 telescopes into one gigantic virtual telescope. So each of the telescopes has a different distance on purpose from each other, so you can cover different baselines here. And the virtual telescope in the end, which you get, is basically the largest baseline you have between the telescope 1 here and telescope 4 here, which is 130 meters. This is something you could not possibly build out of a normal mirror. The telescope would collapse under its own weight. But as a virtual telescope, as an interferometric telescope, you can achieve these large baselines. And that's, of course, precisely what we want to resolve the galactic center. The light is guided from these mirrors down the telescope underground and is combined in here in a small hut on the platform in the instrument Gravity, which looks like that on the right side here. Combines the light of all 4 telescopes, and you get a resolution, and you can, oh, sorry, I don't see half of it because my face is somewhere in the middle. Okay. You can resolve something like 3 milli-arc seconds with Gravity in the end. And as I said, Gravity was actually designed to resolve in particular the galactic center, but I'm coming to that in a minute. First, I think I should tell you how Gravity actually works. And for this, I have 3 figures, and all of them show exactly the same thing in different levels of complexity. So let's start with the picture on the left side. On the left side, what you see is 2 telescopes. Oh, sorry. 2 telescopes, one on the left and one on the right. And you see a point source. Point source, it's a star, it shines light. The light spreads spherically around the star, but it is at a large distance from Earth. So by the time the light arrives on Earth, we actually have a plane wave. And this plane wave, it hits first one of the telescopes, and then after a short time delay, it hits the other telescope. And this time delay is something that has to be corrected underground. So as the light is being guided down through all these mirrors, there are about 12 mirrors of varying sizes and varying functions. The light is guided down into a tunnel, into something called the delay line, which is written here, delay line. And this delay line, you have to imagine this is a tunnel with a cart, and on the cart, a cart on wheels, and on this cart there is a mirror. And this mirror is moving throughout the night back and forth and is correcting the distance here between the light arrival time. Because of course, as the night progresses, the star changes on the sky. It assumes different angles, and as the angle changes, the arrival time between the telescope changes. So the cart underground has to move back and forth, and that's what it's doing all the time. So in the end, you have kind of adjusted light wave packages, and they are being guided into the beam combiner lab, the green square you see here in the figure, and that's of course precisely gravity. So the green square is gravity, and you combine the lights from the 2 telescopes, and of course you combine the lights of all 4 telescopes. So for 4 telescopes you have 6 baselines. So in the end we get 6 quantities. So we measure 6 fringes. And fringes, this is this interference pattern, which we measure in the gravity detector. The physical quantities are the phase shift and the visibility, and that's the purpose of the two other figures to the right side here. This is again the two telescopes which collect light beams, and they have a different path length, so they're different. And what we do now with these delay lines, which I explained, is we put these two these two lines on top of each other, so to say. So that's the initial status. And then when we then still measure a phase difference, although we corrected everything, it means we know something new about the source. The other thing we can know about the source is the size of the source. And the size of the source you measure with something called the visibility. And the visibility is in principle the fringe contrast. So this is shown in the bottom figure. You have again light coming now from the left. It goes through the slits. It produces an interference pattern with a peak in the middle. And then there are secondary maxima and minima to the left and right of it. And at the place, at the size where these, where the pattern vanishes, where you have 0, this gives you an angle. And whenever you have an angle, you already know now where this is going to. You have the angular size of that thing you measured, of the target you measured. And that's, of course, what is interesting to know. However, if you have a point source, the size is maybe not the most interesting thing of the point source because it's a point source, but you can get from this, of course, then the position. And that's what we want to do in the galactic center. We want to know to absolute highest precision the position of the star S2. The orbit of S2 is here schematically as a red ellipse shown. And now, S2 in the galactic center, the size of the S2 orbit in the galactic center, it corresponds roughly to the size of a football arena seen on the moon, seen from Earth. So this is the kind of resolution we want to achieve, a football arena on the moon to get the orbit. But we don't only want to have the orbit resolved. We want to see the star as it moves on the orbit on a daily or nightly basis. And this means we need actually to have a precision to resolve a €1 coin on the moon. So that's what gravity does. And it needs to do that. As I mentioned, it needs these 4 8-meter telescopes, but it needs also something else. It's not enough to have 4 large telescopes at a good separation. You need some other tricks to do that. And on the one hand, you need something called a fringe tracking system. And this works like that. You observe always simultaneously 2 targets, actually. You observe your main target, here the red star, the red blob. That's your science target. That's the thing you want to observe. And then at the same time, you use a star that is slightly brighter, and you observe this one at the same time, and you collect the fringes, and it's kind of correlated in the booth inside gravity. So it helps you stabilize the fringes of the faint object. And you connect this and you measure the separations at all times. And this allows you to integrate for a longer time on a faint object. So you can integrate with gravity on the galactic center for something like 5 minutes in one go. And that's comparatively long, actually. We're talking now about infrared wavelengths. The other trick you need is something called adaptive optics. And to do that, you need an extra star. So there is something called a natural guide star, which is a very bright star, which is somewhere also nearby your target. And there is a wavefront sensor in the telescope. In each individual telescope, there is something called a wavefront sensor, and it measures this wavefront, the plane wave that comes from that particular guide star. And this wavefront is being distorted by the Earth's atmosphere. It fluctuates at all times. And then there is at the telescope level, there is a deformable mirror which corrects in real time all these turbulences, all these distortions. So this is something that operates on a millisecond level. So this is very an intricate system. And if you don't have a natural guide star, you may always produce an artificial laser guide star, but this is something I will talk about later. So you have these two things. You have the fringe tracking system and you have the adaptive optic system. So now you need some people in the control room, and this is how that looks. There is a large control room with separate booths and corners for each individual telescope, because each of the 8-mirror telescopes has its own scientific instruments attached to them. And gravity, which connects all the 4 of them, is just one of the instruments really in Paranal on the mountain. And we have our VLT iBooch for very large telescope interferometer. And all these screens you see here, they all belong now to us, so to say. So each telescope gets a monitor. The guide star is being monitored. The adaptive optics is being monitored. The fringe tracking system is being monitored. Well, really, there is the gravity, the control computer here in the corner where you see Frank Eisenhower. This is the steering, so to say, where you give in the coordinates and the observation blocks and how long you have the exposure and everything. And then you recognize perhaps Frédéric Vincent here, and that's my place. And we're sitting here at the corner of everything, because in 2017, we were hardcore theoreticians. We had no idea about observations. And the only thing they allowed us to do was to reduce the data, which is basically hitting a button on the computer and letting the reduction pipeline run. And then we were crying for help. Frank, what does it mean? We see visibilities and we see phase shifts. And then people explained us what it actually means. And this is how we learned more about the instrument. And then, as you see on the right side, 2 years later, I'm actually sitting at the steering, because in the meantime, I have learned how to observe with the VLTI. And I'm sitting here with Guy Perrin from the Paris Observatory. And the reason we are doing this strange yeah, it looks like we're warming our hands or something, is we observed just right then, we observed a flare of such a star. And always when a flare is observed, that means we observe actually the gas directly from such a star. We take our sunglasses and we have some fun and we celebrate it. Flares are important actually to observe. It's not only the star that is interesting, but also the black hole itself, of course. The cool thing about gravity is that we see the black hole, such a star, we see it at all times. Whether it's flaring or not, we always see light coming from the heated gas from the galactic center. And that allows us, of course, then to use it as a reference. And we can calculate the separation vector between the galactic center, light emission, and S2, the star. And we can do this every night we observe, and we see how the separation vector changes and how S2 actually moves around the galactic center. So that's one of the things one can do, probing the galactic center here, either with stars, observing how they move and calculating their orbital properties out of it. And the other thing is, as the right image is supposed to show, that you have variability coming from the galactic center, and you can observe this variability. On the one hand, it gives you this separation vector, but on the other hand, it also shows you this, this heated gas itself, it moves around something. And that I will show you in a little bit. Just to summarize the previous results in 2020, Andrea Ghez here on top and Reinhard Genzel, they received the Nobel Prize in Physics for kind of proving that really in the galactic center there is a 4 billion solar mass object. They on purpose didn't call it a black hole because it is not quite sure what kind of a dark and compact creature it is, but for all intents and purposes, I mean, it really behaves like a Schwarzschild black hole right now. Or it probably rotates, but that's yet another topic. And Roger Penrose got the Nobel Prize in the same year for the mathematical formulation of stellar collapse and the formation of a black hole horizon. So that was that. very important for this Nobel Prize was actually the following result, which we received, or which we obtained in 2018 already. And this was the measurement of the gravitational redshift. The gravitational redshift is actually one of the 3 classical tests of general relativity, which have already been devised while Einstein was still alive. That was the gravitational redshift, the precession of orbits, and lensing of light. These are the 3 classical tests. So this is one of them. The star S2, actually, indeed, the light of it shifted towards the red, and the gravity instrument was important to measure this, although gravitational redshift is actually, that's a spectroscopic effect. You measure it with a spectrometer. In our case, it was called Symphony, which is also an instrument located at the Very Large Telescope in Chile. You measure the radial velocity of the star, actually. And you do that by looking at the bracket gamma line. The bracket gamma line is, well, it's one of these transitions, right? It's transitions from the excitations levels 5 and onwards back to the level 4. So not to the ground state, so that's an excitation, higher excitation level. And it happens at an energy of 2.16 microns. And this is exactly the K-band, the sensitivity range of gravity. Gravity operates in the K-band, which is between 2 and 2.5 microns. So on this bracket gamma line, it falls precisely in there. We cannot actually observe it with gravity because we observe the galactic center in low resolution mode because it's really faint. But with Symphony, you can resolve this line beautifully and you can measure how broad it is. And from how broad it is, you can get a sense of how redshifted it is, and it gets redshifted as it approaches the galactic center. And in the end, this results in residuals that look like these peaked curves here. What you do to get these residuals is you take the GR orbit, the GR velocity, and you subtract the Keplerian orbit from it. And as a residual, you get this kind of peaks, and the data and the predicted residuals, they really lie on top of each other. This is already on the right side. You see our results from the extended ones, which go to 2020 in this picture, but also the other group around Andrea Guess. Here, a paper by Tuan Do and collaborators from 2019. They observed precisely the same thing. And this is, of course, the genius thing. You have 2 completely different experiments, 2 different telescopes, and you measure the same effect. So that's science, I would say science at its very best. We also, in the meantime, measured the second classical test, which is the Schwarzschild precession. And this is now really a purely gravity measurement. I mean, a gravity-dominated measurement. You still need, of course, the radial velocity, but this is something you can actually see on the sky. You see a difference here in the small square to the top left of the figure on the left. You see the gray dots, the gray data points, they are from 2005. And then 16 years later, the star S2 went all around such a star, again at the similar position, but now shifted. There is a difference in right ascension. Right ascension is here the quantity on the horizontal axis, declination on the vertical axis. And you can do again the same thing. You can take the GR orbit and you can subtract the Keplerian orbit, and what you get as a residual is the figure shown here on the bottom right. So without GR, you would get a very strong drift in right ascension here. So it tells us that we really need GR to describe the S2 orbit. And then there is, of course, not only S2. Oh, in the middle, of course, gravely exaggerated, but gravely, but beautifully, the Rosetta, how you can imagine what this motion of S2 around the black hole. Yeah, and then there is not only S2, of course, there are a bunch of other stars. In the galactic center, we know about 100 named stars, each of them S something something. They belong to a small and dense cluster called the S stars. They're predominantly very young stars, a few million years old. They are typically about around 10 solar masses. And then there is a bunch of older stars, there are fewer of them. And these older stars are typically, they have around 1 solar mass or a bit less, and they are rather faint, red, smaller red stars. And then there is, of course, the question, where do these stars come from? But that's really another topic. What I want to show you here in this talk is that you can follow these stars. Oh, I don't know, this is flickering, this image. This is supposed to, do you see it moving or just flickering? I don't know. What the figure on the right is supposed to show you, I can't really seem to stop it. It's supposed to show you the motion in a more or less smooth way, sorry about that, I don't know what happened, of the star. Yeah, never mind. Maybe I will go just to the next slide and show you what I'm meant to tell you. We have different stars, and some of the stars go far closer, actually, or not, a little bit closer to the black hole than S2. But they are on much longer orbits. So S29 approaches such a star to about 14 milliarc seconds, while S2 approaches it to 17 milliarc seconds. But because S29 has a longer orbital period, it's not as interesting as S2 with its 16 years. S29 takes about 90 years to go around. But there are stars on shorter periods like S55, but then again, S55, that's the one in green, it doesn't go that close to such a star. And then, so I will stop that now. And then we discovered last year, there is also a new star. We started mosaicing the galactic center. So all these gray circles, they are a pointing. So we're taking exposures from that pointing. We take these 5 minutes exposures, and sometimes we just point into the dark where there is nothing. Sometimes we point to stars we know that there could be a star. And while pointing into an area where we knew there were not many stars, we saw, there is something really, really faint. And the next month it was still there, but it moved a bit. And that's the star, the magenta star S300. It's also shown in the right picture here. The 3 different colors stand for 3 different months. So it moves, it has nothing to, it's not a spectral color or anything. It's just a temporal color. It moves between March, May, and July. It moves from red towards green, towards blue. And you have such a star here in the middle. You have S29, which moves really fast with 9,000 kilometers per second. It moved last year around such a star. There is a faint star, S62, slowly approaching such a star. There was S55 also going around a bit slower around such a star. And then there is this faint star, S300. The reason we do this mosaicing and this search for fainter star is that with the current stars, it's not really possible to measure the black hole spin in a reasonable amount of time. You need at least 3 orbits of S2 around the galactic center to say something about the spin, because the spin is an accumulative effect. It will affect the orbit of S2. With every orbit a little bit more, it will get an additional kick. So if you have a star that is like 10 times, for instance, closer than S2, this would speed up things, and it would allow us to measure the black hole spin in a reasonable amount of time. So we are looking for faint stars near such a star. And what we found so far is S300. S300, it seems right now as if it moves with a linear motion away from such a star. So that's not precisely the one we were looking for, but there is potential. So we can detect fainter stars, and there is hope that perhaps if there is something, that we might see it. We don't know, of course, whether there is something. A short word about flares. Flares are these recurring bursts of radiation in infrared, but it's also seen in X-ray. They last for about 20 minutes to an hour approximately, which makes them very interesting because that's the time scale of the innermost stable circular orbit. And we're not 100% sure yet what it actually is, this flary stuff, but there are some reasonable models that might be useful to describe this flaring burst, and that is something called the magnetically arrested disk, which is a model where there is a strong magnetic field that basically inhibits the direct flow of matter onto the black hole. It stops it for a while. The flow is getting somehow entangled with the magnetic field and is being released via magnetic reconnection as something like a hotspot that then spirals onto the black hole. And this is something that could be a good explanation of what really happens, because what we see is when we look, so on the top left, that's a simulation of a hotspot in red that goes around the black hole. What we actually observe with gravity is that there is the photocenter that moves somehow around in a clockwise motion. In this case, that's very nice data from 2018 when S2 was at the pericenter at its closest approach. We measured similar flares also last year and then actually in every year, but they were not that clear and they were much harder to analyze actually, because the farther S2 gets from such a star, the more difficult it is to calibrate things and to know what is really going on. So that's actually work in progress still to analyze the flares that happened since 2018. On the bottom left, you see that during this flare, you see not only the source of light that moves within the period where we observe it, like for an hour approximately, we also see that the polarization changes. Gravity, it can measure two types of polarization. It can measure the P and the S, so the perpendicular and the parallel parts of the polarization, and we see the polarization changes. And this is also indicative of the presence of a magnetic field, and in particular of the presence of a more or less colloidal magnetic field. There is some inclination allowed. The inclination which we think is the best fitted one is a rather low inclination. And then, as you know, comes the Event Horizon Telescope, and it says, yes, we are somehow observing the black hole shadow here at some kind of a low inclination, which is of course fantastic for gravity, because that's the place where we really agree. And the Event Horizon Telescope sees a luminous ring of gas with a dark area in the center. It's not EHT, and Maciek will correct me, of course, later. EHT is not, it's not possible to give the spin a number and say, oh, right, the black hole rotates with this and that. It's rather, it's possible to say that it most likely rotates and it has most likely this lowish inclination. And just to show you where we are with the gravity observations, I show you here plotted over it, just the same figure, just as right above where we observe light. And that's actually a very good match. So we see light, EHT sees also light from the galactic center. This is more or less in a similar location. So we are actually delighted really to have these results now. But enough about stuff which are deep in the galactic center. Maybe just one thing. This is actually my project. I have been working on intermediate mass black hole, and I was trying to find out, is it possible that the galactic center could have an intermediate mass companion? And S2 orbits perhaps around this massive intermediate mass binary. And the answer is, well, the question was, first of all, the question was, how massive could it possibly be? How much mass is allowed in form of a one companion black hole? And the answer is the mass is most likely smaller than around 2000 solar masses. Otherwise, we would have already seen it with the S2 orbit. But the S2 orbit is very well described by just GR and just a black hole and nothing else whatsoever. So formally, there is no need at all for an intermediate mass black hole. However, if we insist and we say, okay, what if, then it would have to have a mass of less than around 200 solar masses. what the S2 orbit cannot really constrain is if the black hole is far outside the S2 orbit. So it can chiefly tell us if the intermediate mass black hole is somehow crossing the orbit or somehow in the middle of it. But this is stuff for a whole different talk, and I will now focus on other highlights. That's actually why you came to listen to this talk, I guess. With gravity, one can actually go to new worlds, like literally new worlds. Gravity is able to directly observe exoplanets. The way it does it, we already have to know that there is an exoplanet. Actually, we have to know where to look. It's hard to just point into the black and then to see something. That's with gravity, that's a tricky thing. But if you know there is a star, and in this case, the first target was Beta Pictoris and its planet B. If you know there is a star and it has, you know it from radial velocity measurements that there is a planet around it, or perhaps two, then you can point gravity to it and you can see binary signatures in your closure phases, the phase measurements that gravity does, and you can see it in the visibilities that there is a secondary object, and you can determine very precisely the position then of this exoplanet. And then of course you can determine the mass and everything, but that's not everything. Gravity has different resolutions, as I mentioned, and the galactic center, you do it at low resolution, you don't really get a spectrum out of it, but you can switch to medium or even higher resolution if your target is bright enough. And stars and planets, which are illuminated by the stars, they're actually bright enough. So with gravity, you can measure stellar atmospheres, and that's really cool. There is a small spectrometer on gravity, again, operating between 2 and about 2.5 microns. And you see emission and absorption lines in an exoplanetary atmosphere. And what is interesting there in these planetary atmospheres is that you have absorption lines of carbon and of oxygen. And then if you know or have heard talks about planets and exoplanets and planetary atmospheres, you know there is this very important ratio of carbon to oxygen. This ratio, carbon to oxygen, it tells you about the formation of planets, how they formed, because it is not obvious how they form, whether there is an accumulation of dust, or whether it perhaps works with ice granules. And then with gravity and also other instruments, you see, or at least in this case, you see that you have a comparatively low carbon to oxygen. It says 0.44. It's measured, I think it's the reference is the solar system planets. So in comparison to solar system planets, you have a much lower ratio. And this tells you that in this case, you have a formation process that is dominated by core accretion, but with a strong icy planetesimal enrichment, because you have enough oxygen and in the game to conclude that there is icy granules involved. And then, of course, if you look at other systems, there maybe you will get a different result. So that's interesting how these hot Jupiters and other planets form. Another completely different topic, but equally exciting, is quasars and AGN. The first object of this kind was the quasar 3C273, which has been observed with gravity, and gravity was just pointing to check. Okay, we can see it. We can collect photons from that one, and then what they noticed is, look at that. In the broadline region, there are different movements. Some parts seem to go away from us, and some parts seem to come towards us. So there was a very clear signature that the broadline region in this quasar is actually associated to a rotating disk. And now when you have a rotating disk, you are able, of course, to measure the mass of the central object. And then they could determine a mass of 3 × 10⁸ solar masses for this particular object. And this was the first of many. So they then, this part of the gravity team went on and measured many quasars, many masses, and they they align with previous measurements with other methods. But gravity, of course, again, is a very precise way to measure things. So that's exciting to have gravity in the game of quasar mass measurement as well. And then there is the AGN NGC 1068. And there, gravity was able to resolve the dust region, because in infrared, you have mostly warm dust that emits light. And they noticed that this hottest dust, it does actually not belong to a geometrically and optically thick torus, because often when you have these schematic representations of AGN, there is this huge dusty torus around it. But apparently, this is not really an extremely geometrically thick and optically thick torus, but rather kind of a patchy and rather thin thing. So what they measured is they measured the inner rim actually of a thin gas and dust disk. So instead of an optically and geometrically thick structure, you have rather a thin, dusty environment. This is overlain with these blue other measurements, and the ellipse in the middle, this is represents the dust sublimation area. I guess, actually, since Christoph Nalevaiko is here, I guess he's the expert on the matter. Maybe he would like to tell us afterwards something more about that. Another and yet entirely different topic for gravity are the young stellar objects. And there, gravity is able to resolve the magnetic, not the magnetic field lines per se, but the accretion via magnetic field lines from the disk onto the star. So gravity can resolve these arches where matter spirals along the magnetic field lines and hits then the star. So this is, again, this is very strongly seen in the infrared. And I think that was even a Nature paper, because they could show that stars, young stellar objects, they have these strong magnetic fields, and matter is indeed being accreted via these magnetic fields. So that was a very beautiful results as well. And then, of course, gravity can see with its high resolution spectral mode, it can see all the stars, and it can see in the infrared precisely the gas morphology, where is what is shocking with which part, are there ejections, are there streams of jets and stuff. And one of the prime targets was Eta Carina, but interestingly also a high mass X-ray binary, namely SS433. It's a high mass X-ray binary where the compact object, it's not clear whether it's a black hole or a neutron star, still not clear. Also, gravity couldn't resolve that, but gravity can see at least the outflows and inflows of matter in this system. Also related to stars, there was a group who used gravity. So that's now not the gravity core team, which I showed you the pictures from, but just a different group who asked for observation time with gravity, and they measured two microlensed images of a star and could calculate from that the Einstein radius of that particular star. And then another thing which is really very typical, whenever gravity looks at one star, it sees also another, which means most of the star really, and it's not only in Orion in this trapezium region, it's also in the galactic center. Most of the stars have binary companions or triple companions, which tells you again then something about the star formation processes. So most of the stars are not single lonely stars. And then to come to an end slowly, I would like to tell you something about where do we go from now? Now we discovered all these things, all these fantastic things about different sources. Have we seen everything now? Could it go further? And the answer is yes. On the left side, I show you how the VLT looks right now, or I don't know, not right now, of course, but today. And this is, you have 4 telescopes, and one of them, telescope UT number 4, it has a laser. When you see the laser, you know 100% it's not a gravity observation going on, it's something else. it is an observation that uses just one of the telescopes, namely the one with the laser. And the laser is creating a laser guide star. So this works like the natural guide star, which helps you to do the adaptive optics corrections. So to correct for atmospheric turbulences, you shoot a laser into the upper atmospheres in about 90 kilometers. It interacts with the atoms in the ionosphere. And you can tell from the light that's coming back from this reaction, you measure again with a wavelength sensor, you measure the turbulence and you correct it. And then you can use precisely the one instrument that is attached to this telescope to do your observations. The instrument is called MUSE, I think. Now, what we want to do with gravity is we want to use these laser guide stars to create artificial guide stars where there are no natural ones available. So to do that, each of the telescope has to be equipped with its own laser. So this is now a major, major upgrade of the entire VLT that is going on right now. It will be finished in 2 to 3 years. So each of the telescope will receive its own laser. And then it means that you can do interferometry, infrared interferometry with laser guide stars. And what this helps you is you can look at targets where there is no ideal guide star. And this happens in our case, especially when we are looking at AGN and quasars, and we're looking back in time to some redshifts, 0.4 or larger, 1 and further. It's very hard to find suitable natural guide stars. So it is important that we can create an artificial guide star. And so this whole upgrade, this will help us mostly to look at AGN. But in general, the entire upgrade, it has many steps. It includes off-axis fringe tracking, which is already working now. The upgrade goal has already been fulfilled. NGS stands for natural guide star, LGS for laser guide star. So this helps you also to go to ever fainter targets. The performance gain, the expected performance gain is that we can go down to K magnitudes of 22. For a comparison, S2 has a K magnitude of 14. The faintest star we have observed so far is S300. It has a K magnitude of larger than 19, more like towards 20. And so this will add to 2 orders of magnitude, basically. And so in future, we should be able to observe, for example, binary black holes, binary AGNs at the redshift larger than 1. This also helps the exoplanet search. For example, right now, gravity can see in particular hot Jupiters. These are, because they're hot and fairly young, they are fairly bright, so gravity has no problem spotting them. But if we wanted to observe super Earths, which is of course way more interesting, because the more similar a planet is to Earth, the more interesting it is to know about planet formation and atmospheres and what is going on. So with the updated gravity, it's actually called Gravity Plus, the upgraded instrument, then there is a chance that we can observe many super Earths, actually. And then, of course, going to fainter magnitudes should help us detecting that fainter star around the galactic center we're hoping to see, if it exists. And with that, I would like to conclude and open perhaps to comments and questions from the colleagues. Thank you very much.
Thank you very much. So I'm clapping on behalf of the others.
Yeah, thank you.
Do we have any questions, please?